Welcome back. Today we're going to be looking at other types of functions, a little bit about evens and odds, symmetry. It won't be too crazy, so let's go ahead and get started. Let's get started with the creed. Remember, the best way to do good in class, say the creed. Today is a new day. I can read and remember well. I can develop my viewpoint and apply it correctly. I have eyes to see, ears to hear, and a mind to understand. It might not be easy, but it is worth it. All right, let's get started. All right, so today we are going to be looking at other types of functions. We're going to be looking at 2 or 3 different types, some characteristics of graphs, that kind of thing. So let's get started. We'll go pretty quickly because the first topics aren't that wild. So the first thing starting off, we're going to be talking about increasing, how an increasing function looks like that, decreasing, how a decreasing function looks like this, and constant, and how a constant function looks like this. Whoop, like perfectly straight line. Worth noting, there's that fourth type of line that's not a function, not function, but it's an undefined line, right? And think about it as you're reading from left to right, walking upstairs, walking downstairs, or walking flat on the ground. That's kind of increasing and decreasing. So let's look at this real quick and just see, all right, can we identify the types of intervals? This looks like it's going down, and I always do red for down. I'll always do green for up, and then we'll go back down and say red again, right? Can I identify those intervals? Can I use what we learned in the past classes to write that interval? Well, the first red interval looks like it goes from negative infinity. It goes down, 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 and then boop, stops at 0. The next green interval looks like it picks right up where that left off, goes all the way to 2. And then the next one, and looks like it's decreasing from 2 to infinity. All right? Worth noting, if you can do that, you might be able to write it in set notation as well, where x is a number that is bigger than 2, but smaller than infinity. That's an important thing to remember. Let's go ahead and do one constant. If you look at this next one, we've got one constant section right here, where from negative infinity all the way to, looks like 0, we've got a constant function. Okay, so I'll label these 3. This is increasing. Whoop, I lied. Red is decreasing. Green is increasing. Blue is constant. All right, not too crazy. Hopefully you can work through those and kind of see how to write them in interval, write them in set, and look at a function to kind of know what's going on there. All right. Worth noting, the reason why we call it increasing or decreasing is because as x increases, what is y doing? Well, y is increasing for an increasing function, right? And y is decreasing for a decreasing function. Another way to write y, so your brain can be thinking about it, is f of x, right? As x is going up, y is either going up, going down, or staying the same, and that's why it's called increasing or decreasing. All right, so let's look at this real quick. This relative min and max we're going to cover in a different section, but it's worth looking at and saying, can I identify a relative max, looks like that, and a relative min, looks like that. We'll go back up on this graph and we'll say, yeah, look at that. Look at that third one. Boop, boop. I see what looks like a relative max and what kind of looks like a relative min, right? Awesome. So we're looking at the types of functions. We're saying increasing, decreasing, maxes and mins at those turnaround points. Let's see what else we got. Next thing we're going to look at is kind of conceptual, so it's important to think about. And it's this idea of symmetry. Like back in the 3rd grade or whatever, when we talked about shapes. When we talked about a shape having symmetry, we would say we were going to draw a line through that symmetry, and then say like, okay, well this blue half of it, if I folded it over that line, would it line up perfectly with that green half? That's kind of that idea of symmetry. Yeah. And thinking about, okay, so if we look at a triangle, let's think about that. If we look at a triangle, that's the easiest way to show like, oh, symmetry or not. So if we look at that triangle, boop, 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 and we fold it over itself, then it's going to line up perfectly. But could I draw a line that doesn't? So look, if I draw this line and I try to fold this blue section over, right? It wouldn't line up perfectly. So that's kind of what we're thinking about here. And you could think about a normal function. I don't know, think about the parabola. Can you think of a line where the parabola folds over perfectly? Well, that one's a little easy and it's kind of obvious, right? So that's what we're going to see. And here we see the conditions for that symmetric thing is just plugging in a negative for where you usually have a positive. So plugging in a negative x, negative y, or negative both, which is origin symmetry. So let's look at that real quick. So think about the normal function, and I'll do these in different colors. This is the normal function, right? Think about what happens if I plug in a negative for that x. All right, well, we can rewrite that as negative x times negative x, right? And then we can rewrite that as negative 1 times x times negative 1 times x minus 1. And then one more step, we can rewrite that as negative 1 times negative 1 times x times x. I know that's a lot of work, and you don't have to do this every single time. But then we can kind of see what happens to those negative 1s. They cancel out, right? Or they don't cancel out. They multiply together to multiply into a positive 1. And we are left with x squared minus 1. Boop, boop, boop. Awesome. Now the question to ask yourself is that the same as the original function? X squared minus 1, x squared minus 1, check. Same as the original function. Awesome. All right, well, I guess we got to check the next few. So let's look at y equals, and now we're saying x squared minus 1. That's the original function, right? And we're looking to see if those two match up. They did. So what are we switching the second time? We're switching the y for negative, right? So negative y equals x squared minus 1. Well, then I'm going to turn that into y equals, and I'm dividing by a negative 1 all the way across, right? So you get negative x squared plus 1. I'm going to pull out that negative, and I'm going to say that equals negative x squared minus 1. Well, that's literally the exact opposite, right? That does not equal x squared minus 1. It's actually the opposite across the x-axis. Oh, well, that's what symmetry it would have been, right? So that number is not the same, right? Because if we plug in a 1 into the original function, we would have got 0. Oh, that doesn't work. If we plug in a 2 into the original function, we would have got 2 squared is 4 minus 1 is 3. If we plug in a 2 into the second function, we got 2 squared minus 4 is 3 with this negative sign outside of it. And that's not good. Those are not the same. All right, last. So that's not the same. So that means not symmetric x-axis. I probably should have mentioned this when I did the first one. That check mark right there means that it's symmetric for the y-axis. Awesome. Last one. We're going to switch both signs now. So y equals x squared minus 1. That's the original function. Here we go, switching both signs. Negative y equals negative x squared, minus 1. Oop, missed my parentheses. Negative x squared minus 1. All right? I'm going to start by dividing by negative 1 across the whole thing and get y equals negative x squared, negative x squared plus 1, right? I'm going to take care of that inside the parentheses sign and get negative x squared plus 1. I'm going to pull that negative out and get negative x squared minus 1. And that is not the same again. That's actually the same as the second one. So that does not equal x squared minus 1. So not origin symmetry. So that's just the check for symmetry. But it's actually going to get a lot simpler as we move on because we're going to be able to do it a little bit quicker with this second method. So I think we're going to look at a graph real quick. Absolutely we are. And we're going to say, what do these look like on a graph? What do those three things, origin, x, and y, look like on a graph? Well, what we're going to do, I'm going to go ahead and do the middle one first because you can kind of see what's happening. If you draw this line down the y-axis, and you pick any point, and you go to the line, and then you draw the same one, you get a point, right? You get a point on the graph. Pick this point, go over there, draw the same distance, boop, boop. So that looks like it's symmetric. So symmetric with y-axis. Well, let's check the x-axis real quick. If I draw down to the x-axis and I keep going, no, there's nothing down there, right? Nothing at all. Okay, well, what about origin? Let's check origin. If I take this line and draw it to the origin, and then I keep going, anything down there? No. So that's just a y-axis check. And then up here above, it says, okay, well, what happens if it's symmetric with the y-axis? We call it something now. Symmetric with respect to the y-axis, from now on, we're going to call even. And we'll see why in 1 second. So we're just building the framework for what this thing is. That's even. All right, let's check out this origin one right here, where I'm going to take that origin, or the 0, 0 point. I'm going to draw a line to it, and then I'm going to draw that same line on the other side. Boop, lines up perfect. Same thing, I'm going to go here. Boop, boop, lines up perfect. What about this one on the x-axis? Looks like about 1 away. Boop, boop, lines up perfect. We call that origin symmetry. And if you scroll up, that's going to be odd. So we've got evens and odds as a new definition for the same thing. Easy to remember, origin starts with O, odd, right? Not too crazy. All right, what about this one? Well, put a little dot here. Go to the origin and keep going. Nope. I'm not going to do x because there's an x on the graph. So that red line means not origin. Well, let's try the y-axis. Let's start right here. Boop, boop. Well, that green line means not y. So it is neither even nor odd. Okay. Now let's see. Now we're going to get to see why this really matters. Why do we care about this? So if we scroll down here, we see, hey, guess what? If we switch out the x's with negative x's and the right side of the equation doesn't change, that's an indicator that it's even right away. And if we switch it out with the negative x's and every term changes, every single one, that's also an indicator. And then if it's like maybe half and half, that's a neither. So like, oh, what does that mean? Let's go ahead and look. All right. So I'm going to plug in my negative. F of negative x equals negative x cubed minus 6 times negative x, right? I can already see what's about to happen. I'm going to get a negative x cubed plus 6x. Well, look at those. Both the signs changed, right? Because of that negative sign, because of that positive sign, both signs change, right? And if both signs change, that means we are looking at an odd function. And we can use that odd function to tell us what kind of symmetry it is. Odd, origin, because both those O's, right? So origin symmetry. All right? Well, what happens if we do the flip-flop? What if we plug in that negative x, but we get something different? What if we get negative x to the fourth minus 2 times negative x squared? And we see that with those evens, they're just going to cancel out the negatives, right? The negatives are going to go away because if you do a negative to the fourth, it's just going to be a positive. So you get x to the fourth plus 2x squared, right? Well, they both stayed the same. Those are the exact same function as the original one. So because it's the same, we can do this like boom, 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 boom. Oh, why did I say plus? That's a minus. I don't even know why I wrote that down. It was a minus above, it's still minus. You're probably yelling at the screen saying, hey, it's minus. Okay, so because both the same means even. Means, what did we say that meant? That meant y-axis symmetry. And the cool thing about that is look at the exponents of everything. Look at the exponents of it, and this is going to help us. Look at the exponent here. 3 is odd, right? 1 is odd, right? That's nice. Look at this. 4 is even. 2 is even. That's nice. That's kind of indicative of what's happening. So you can guess what's going to happen here with a 2 and a 1. We've got an even and an odd, so it's not going to work out nice, right? We'll see real quick, and then we'll move on. Negative x squared, that's going to stay the same, right? But 2 times negative 1, that's going to flip signs. And we're going to be 1 times negative x. Negative 2x plus 1. Well, we had 1 stay the same. We had 1 flip signs. And we had another stay the same. So because it's just not consistent, it's neither even nor odd. All right? All right. Let's keep going. We're going to look here at piecewise functions. I'm going to do 2. I'll let you do 2. So piecewise functions are just like functions, but with a condition. And before we take that condition, we're going to take that number, and instead of just plugging it straight in, we're going to take a pause, and we're going to say, hey, where does that go? Which one makes more sense? Does it make more sense that 30 is in between 0 and 60? Or that 30 is bigger than 60? Well, 30 is not greater than 60, so I'm going to cross that out right there and just say, I'm going straight to that function right there. There's my function, plug 30 in. Nope, there's nowhere to plug 30 in, so that is my answer of 20. All right? Not too crazy. Watch this. We'll do the exact same thing. Take this 100, plug it in. Does it make more sense that 100 is in between 0 and 60? That doesn't make sense to me. Cross it out. Or 100 is greater than 60? Well, I would say 100 is greater than 60, so I'm going to plug it in for t right there. And I'm probably going to get something like 20 plus 0.4 times 100 minus 60, which is 20 plus 16, right? 40 times 0.4 is 16 equals 36. Awesome. And that's kind of how piecewise works. You take the function, you take the number you're plugging in, and you check which one works better, top or bottom. Usually there's 2. Sometimes you'll see 3 functions. So I'll let you go ahead and work those next 2, and we're going to move on to something that comes up in math all the time, really important to focus. This difference quotient, this limit definition of a derivative, if you've taken calculus. This difference quotient, or the subtraction of two things that are super similar but separated by an h. All right. I think I'm going to do the first one and let you do the second one. The first one's a little easier, but that's okay. Because the first one doesn't have a squared right here, so you can kind of see the process. And the second one has a squared, so that's going to be on you to practice. All right, so let's do this first thing. Here's how we're going to do it. I'm going to do it real slow. I'm going to put a box around the parentheses, box around where I'm going to plug it in so you can see what happens as I plug that blue box in, right? So this is going to equal 2 blue box minus blue box plus 3. This is so you can see me plugging in the variable, right? So now I'm going to plug in the variable. What's the variable? It's not a nice, neat number. It's parentheses x plus h. It's parentheses x plus h. So that works out to give you something like 2x plus 2h minus x minus h plus 3, right? I know that went kind of fast, but that's me plugging in that blue box into my exponent, distributing, and then we probably get something like x plus h plus 3. Awesome. So now we're going to take that answer. That answer is the answer for our A. I'm going to take that answer. I'm plugging it straight in where I see the same dang thing, right? I see that same thing right there. So I'm going to take that answer, red box it, and I'm plugging it in. X plus h plus 3 minus, and see this orange box? I see that somewhere way up here, right? This whole dang thing is the orange box, isn't it? So I'm going to subtract that orange box, which is 2x minus x plus 3. All right? A little bit of distribution. And we end up with x plus h plus 3 minus 2x plus x minus 3. I distribute it. Remember, we got to distribute that negative sign amongst the parentheses all over h. And we can see some cool stuff start to happen. This will always happen, that stuff starts just canceling out left and right. X, 2x. Those all go away. 3 and 3 go away. And you are left with h over h, which is just 1. All right? Okay, so it's really important. It's really important that you keep your sign straight, that you plug it in. But this is, if you're going to practice any one on the whole assignment by yourself, it's this example 9. Example 9 is the thing to practice. All right. Thanks for watching. Make sure you're practicing all those problems we didn't go over. Make sure you're asking questions, emailing me if you have questions for class. I'm coming to office hours, doing everything you can to be successful in class. Thank you for watching this, and I'll see you soon.